Welcome. Today we're going to be starting in this mini video, starting our discussion of of section 6.5 of your text on improper integrals. And I'd like to start out by just recalling the motivating example from the preview activity. If you have not already done this activity, go ahead and stop the video and complete the activity and then resume watching. Okay, so from the preview activity, you'll recall that you were investigating a function p of t, which described a set of light bulbs that, and in particular described how long those light bulbs lasted. And in particular, the function p of t had the property that the integral, the definite integral of p of t from t equals any a to any other number b was equal to the fraction of light bulbs that fail between time A and B. Let me just give you another way of thinking about that number. You can also think about that as the probability that a light bulb fails between time A and B. So functions like this are called probability density functions, sometimes just density function. And so I'd like to go ahead and write out the definition of a probability density function. And these show up all over the place, particularly in probability, but you use them in a wide variety of applications. And so that's one of the reasons why I wanted to highlight this application of integration here. So here's the definition. If we are given a population with some characteristic x, then a function p of x is a density function for x if the following three properties hold. So the first property is p of x has to be greater than or equal to 0 for all x. The second property, and now this is going to be the integral property. So the fraction of the population with x between A and B is equal to the integral from A to B of p of x. Again, just as before, you can rephrase this as the probability that a randomly selected member has value of x between A and B. Okay. And the third property is the total area under the graph of P of x must be 1. So you can think about that as just describing that the total population is 100% of the population. And I just want to relate this again back to the preview activity, right? In the preview activity, the population was light bulbs, and the characteristic was failure times. So let me go ahead and move on to another example. And so this example is dedicated to my son. So let's suppose we have a density function for the lengths of a toddler's naps. Okay. And so let's call this density function P of t, where t is in hours. Okay, and I'm going to go ahead and just paste in my little sketch of that here. Oops. Let's see. Okay, so let's suppose that this is the density function of Ian's naps. You can see that this does satisfy the properties of a density function, or at least it satisfies the first property of a density function, that P of t in this case is always positive. And if we assume that this is a density function, what we must have then is that the total area under this red curve must be 1. Notice it is in fact 0 outside of the range of 0 to 3. That's because, of course, he can't nap negative amount of time, and I wake him up if he naps longer than 3 hours, or if he's still sleeping at 3 hours, because otherwise he won't sleep at night. So if we assume this is a density function, we know the total area of the graph of P of x is 1, and then the other fact that we know is that that areas, definite integrals of this function, correspond to probabilities that a nap is within some given length. And so let me go ahead and ask you 2 questions that you can answer, and then we'll resume in the next video with the answers to those, and we'll continue on discussing density functions and how they relate to improper integrals. Okay, so the 2 questions I have to ask you are, first of all, find A, so that this is a density function, and the second question is to determine the probability that Ian naps at least 2 hours. And so go ahead and we'll stop the video here and go ahead and compute those, and we'll continue in the next video.